Mas sacanagem. Chefe lá, os caras chegam e voltavam no almoço, sacanagem lá. Aí já ficava lá dormindo. Aí o bicho ficou corrido, a mulher botando uma lata de água. Aí já na porta dele. Vocês estão assustados por quê? Pô, sai um menino, não vai sair uma lata de Coca-Cola?
I've got one. I was just wondering.
Were the other pointers?
With the other pointers, do you have it? Oh, okay, that's fine. No, I just wasn't sure. I didn't remember putting my back in the bag, and then I didn't see it. Well, you guys look much too happy. It must have been a really good lunch. Okay, so we want to pick this up. So we're looking at the linear inverse problem. We're trying to demonstrate a few things through the app. So just to remind you of where we are. So all the things that we're going to be looking at, we're going to when we use the word model, we're going to be talking about whatever function we're trying to find or set of parameters that we're going to try to find. So within the context of inversion, that's what we're going to use for the context for that particular word. The physics that you are working with is going to be described for a linear problem by these kernel functions, and each datum that you have can be thought of as an inner product of your model with a kernel function. So that gives you your data system. Kind of showed you a little bit through the app. So you've got capabilities of generating some combination of a Gaussian and a boxcar. And then when you have got this specified, you also specify your kernels. That gives you your data, and then you can add some noise to it. For us, for the kernel functions, we kind of took our the ideas that we had from frequency domain sounding. We thought about this resolved system, then we thought of sort of a lower frequency that sees down deep, and a higher frequency, which is like that. So, decaying exponentials sounds like a pretty intuitive thing to work with. For the app, you could specify the number of kernels that you want. So that's the n. In this case, there's 3 different values, and for each of those kernel functions, you sort of integrate these functions with the data to get, or with the model to get your data. To actually do that, we broke the model domain up into a whole bunch of cells. In this case, they're just one dimension. They're just layers. So we did discretize everything. So G here, our matrix, is m number of data by m the number of elements. And then we make the data in this form that D is equal to Gm. The observations that you can work with, a good way of working with them is to have, let's say, some sort of percentage plus a floor. So that's a pretty good description of the noise. And what we mean by that is that if you have so your datum is like your observed data is your true data plus some noise. And this noise we're going to represent as being a Gaussian, so n of 0 epsilon. And epsilon, the standard deviation of your Gaussian. So this is Gaussian noise that's got zero mean and standard deviation epsilon. So, it kind of looks like this. So zero mean, standard deviation epsilon. So this is sort of plus or minus 1 epsilon. So that gives you the width of the Gaussian. And so then to estimate the noise, we draw a sample from this and add it to that. The standard deviation epsilon is some sort of percentage. Let's say 5%, so 0.05 times the absolute value of the truth plus some floor, which might be whatever you choose it. So that's how we're going to work with that. To add the noise, and that gives us something now that looks like this. So these are the data that you're going to be working with. Want to catch that? So these are the data that we're going to work with, and you want to recover that. The high impact, at least I hope it was a high impact point that we did just prior to you going for lunch, is that if you set this problem up to just find a solution that fits the data, that you could be quite wrong. Okay, so let's actually take this a little bit more slowly. We're going to set up the inverse problem. So now we've got our observations. They're contaminated with noise. We're going to estimate an uncertainty for those. We have the ability to do the forward modeling, and now we want to do the inverse problem. We're going back from the data to the model space. And for this linear problem, we just write the data as GM is equal to D. And an important thing here is that generally the number of unknowns that we have greatly exceeds the number of data. So when we're working with an inverse problem we saw before, we're actually trying to find a function. And a function has infinitely many degrees of freedom. We're going to have a representation of that with respect to a certain number of cells, but that number of cells is much, much larger than the number of data that you're going to be working with. So it's going to be an underdetermined system. We need to have some kind of a misfit criteria because we're going to fit the data. So as I was just saying here, our observations are the true model data plus some noise, epsilon, and we're going to represent that noise as Gaussian standard deviation epsilon j. And so therefore our misfit measure is this one. It's going to be the difference between the observed and the predicted value divided by our estimated uncertainty. So the quantity that we're going to estimate is the standard deviation of the observation, and we're going to use this as a total misfit. Somebody? If the data errors are Gaussian, zero mean and some particular, well, unit standard deviation. So if there's zero mean with unit standard deviation and the division by epsilon here tries to accommodate that, then we've got a statistical quantity here for which there's an expected value. So the expected value of this quantity here is approximately equal to the number of data. So that's important because we not only need to have a measure of misfit, we need to have a criterion for deciding, okay, when are we kind of in about the right ballpark? When are we fitting the data to a degree about as well as we want? So we're going to set up the problem so that we'll have a target misfit. We're going to use that as phi d star. And we're going to try to find a solution, find M, so that our final misfit is something close to this target misfit. So this is a pictorial of how you can set up the problem in which what people often have done in the past. We've got our observations, and we have an inversion algorithm that adjusts the parameters. We get a model that comes out of the inversion, and we forward model that to get our predicted data. Right? So we've got our observed data, and we have predicted data. And then first thing you do is compare them, and if they compare favorably, you might say, okay, I'll accept that model and proceed on. If they don't compare favorably, then you'll modify it and try to go through again. And we're going to use this quantity here as a misfit. It should be. So as I said, here's our misfit criterion. We've already said there should be an expected value of this that maybe is something in the order of n. But if we forget about that for the moment and just try to see, okay, let's just make this as small as possible, then that brings us to the point where we were just prior to you leaving for lunch. And that's what happened with the inversion app, and you saw that as we fit the data better and better, initially we're in good shape, but after a while we actually do worse because we're fitting the noise, and that requires a lot of structure. Another thing, this has come up a couple of times in the past, and again we'll show that more this afternoon, is that there's non-uniqueness in this problem. And there's a couple of reasons for non-uniqueness. I mean, sometimes there might be just plain physical basis for that. For anybody who's done potential fields, for instance, you know that if you take gravity values over a surface or magnetic values over a surface, that you could reproduce those observations just by having an infinitesimally thin plane of density or magnetic susceptibility. So it's kind of like an equivalent surface, and that's an example of non-uniqueness. There's no inherent depth resolution in that. There's other kind of trade-offs that can happen. We'll show this afternoon in the magnetotelluric problem you get essentially the same data if you have a layer in there and it has a particular conductance in it. So in this case here, so this is depth, and if we have a very thin layer with high conductivity, it gives essentially the same response as a thicker layer with lower conductivity, and so on. So here's the responses that you have from those, and when you add errors to these things, they're essentially the same. In DC resistivity, this is an example. We actually put this together some years ago to kind of quantify depth of investigation. The model here is as follows. The red are conductive units. So they look like, so there's 3 red units up here. There's a long vertical conductor here. There's a short conductor here, and there's a resistive body here. There's a lateral conductivity contrast, so this is more conductive on here, more resistive. And then buried in here, there's a changing overburden as well as a conductor. So it's a fairly complicated system. There's a few things that one one would like to perhaps know about this. One of them was actually whether or not we could see, could we distinguish, for instance, that this conductor went all the way down to depth, and then, or was it truncated? And also then, could you kind of distinguish between, resistive and conductive bodies? So that's the model, and now we take that and we do a DC resistivity survey over top of that, and now we have a pseudosection that looks like this. So first of all, in the pseudosection, you can see that it's pretty hard to kind of tell geologically what's going on. The near-surface conductors kind of result in these sort of banded structures, but it's very complicated. You have to invert those data. The inversion is set up so that you not only reproduce these data in some form, but you try to find a structure that is smooth and sensible. And we do that, you end up with something that looks like this. So that's actually not too bad. The main thing is that you see these conductors up here. You definitely see this break here where we're coming from sort of conductive to resistive. You also see some manifestation of a conductor here. See the resistor, there's a conductor, and there's another conductor. So that's, you got at first order the bulk of some information. This certainly doesn't look exactly like that. And there's ways of trying to tailor the inversion algorithm to give you out structures that have models that have a different kind of feeling and structure, and things that could be more blocky or whatever. There's a few parameters that we'll talk about that could change the structure. I'm going to just show you on the next slide the results of changing a few parameters, and you can start to get an idea of just what non-uniqueness could look like in a non-linear problem. And the three models, so we're going to show this one and just three other models. Those models are all going to reproduce the data. If you look at it by eye, the predicted data are going to be exactly the same as that. So here's the models. If I take this model, or that model, and I do the same DC experiment over top of it, I get data that look identically like this, but these are the different solutions. So that, I think, should make an impact on you with respect to, for a nonlinear problem, just how many mathematical solutions there are out there that will just, if you're just concerned with fitting the data, any of these is equally probable. Okay, so that's what we're faced with. That's a fundamental non-uniqueness that's going to happen in every inverse problem that you work with. And so you need to think about this right up front. So the idea of trying to decide what kind of model, or how do I select from an infinitely many of really crazy variable models? How do I select one that is really meaningful? That is the fundamental thing that needs to be addressed. So let's just kind of look now at this basic problem of non-uniqueness. So we wrote the data as this system here. So here's our kernel functions. We could write it as D is equal to GM. And in the app, we had that M was equal to 100 and n was 20 data. So that we were really underdetermined. We had far more model parameters than we have data. So that's infinitely many solutions. So let's just kind of think about that. I'm just going to grab a little bit of coffee. We've got more model parameters than we have data. So let's think about a simple problem. And the simplest problem you can think about is just a one data problem. So let's suppose we've got two parameters, x and y, and I say, okay, here's my data, it's 2, and I know that x plus y is equal to 2. Underdetermined, more parameters than I have data. What's the solution to that? Well, of course, there is no solution. Any place along this line will satisfy the data. So 0.11, 2.0, any of those are fine. So that's a fundamental problem that we have to deal with. So now we come to this problem like, okay, there's infinitely many solutions. How do I pick one out of that infinitely many? And we basically need to have extra knowledge and extra information. And that can come from a whole bunch of ways. There could be geophysical knowledge. Maybe you know values are positive or within some bounds. So you've got a physical model there, you've got, let's say, seismic velocity. They've got to be positive, you can't have negative velocities, and they're within certain parameters. Okay? So that's a possibility. You might know something about the rocks that you're dealing with. So maybe you've got estimates for the host rock or the halite that Sagi was talking about. You might also have point information from drill holes or physical logging. Okay, so those are one kind of set of information. The other is more of a structural, more of a kind of a philosophical idea about kind of what you want to get. I mean, you obviously have the choice of making something that's complicated, or you could make it something that's simple. So the idea is like, okay, well, if you have a solution with 30 sort of peaks or troughs in it, and you can also have a solution that has one. I mean, somehow the one that is as featureless as possible might be a bit more representative or robust. So that's another kind of thing that you could do. And then there's geologic character, because sometimes we expect things to be smooth. It could be gradational, or maybe it's blocky, or maybe it's sparse. So maybe we could put that information in. Maybe there's scale lengths that are put. You feel like, okay, can I find something that has got a scale length longer than this? Or maybe there's structural constraints. You simply know that, okay, there should be a fault in this area or something like that. So these are like the kinds of things that you need to now start to think about and to accumulate before you even really start to press the button on run the inverse problem. Let's just bring together all of the a priori knowledge that I already have, and then use that to help set up the problem. So now let's think again about this problem of trying to pick a single solution from infinitely many possibilities. And sometimes this kind of resonates. I mean, suppose that you use everybody here, and I'm faced with a with a solution I'm trying to find, okay, so here's my question. Find a person in the room, right? So there's many answers to this, right? So each one of you could be potentially a solution. And that's not enough information to go on. So I need to have some way of identifying each person with a possible solution. Identifying them so that I could look for a particular characteristic. For instance, if I actually use height, okay, as my metric, then put you all up. We could have a ruler, and there would be a person who might be the tallest. Maybe you are, but I'm not sure.
For sure not.
Okay. Well, if you stood on tiptoes, then. So it could be physically the tallest person, or it could actually be the shortest person. I mean, either of those two ends work pretty well if they select one. It could be the person that has got the most hair, person with the least hair, person who's got roundest glasses, anything. So any metric that I can use, we could use to identify or to select one person from this room as a solution. So that's the kind of idea. It's sort of that can sometimes help us as a mental process. There's many solutions, but there's also many rulers. And if I choose the right ruler, then that helps me identify a particular solution, and that's the one that is useful. And we're actually ultimately going to use all this a priori information to develop our ruler so that when we choose to minimize like the smallest element of there, then we're good to go.
I have one question. Because usually in mathematics, this inversion problem, you have two kinds, right? One of that's the one you're showing us. That's the number of unknowns is greater than the number of equations. This x plus y equals 2. It's one equation for two unknowns. But actually, when we go to the seismic world, usually we have the opposite. When you do a seismic experiment, if you take all the number of data that you have, that means the number of traces, the number of samples per trace, all the information that you have, actually the number of unknowns is much less than the number of information that we have. So the problem usually is not that we have infinite solutions, that we don't have any solutions at all, because we don't have one single solution that fits simultaneously all the data. So we need to move to like a least square approach, something that, okay, we can't have one model that fits all equations, because we have too many information, too many equations for a few unknowns. And then we need to choose one model. We select one objective function that, okay, it doesn't fit all equations, but the distance from the solution among all equations is the minimum possible. That's exactly the opposite that this kind of inversion problem. That's the number of unknowns is.
Well, it sort of is. There was a lot of stuff that you just said that we can parse out. First of all, first of all, when you're setting this problem up, you're going to still be dividing things into cells, right? So already that's a parameterization. If you're really trying to find a function, then those cells should be really small, and to help solve that inverse problem, then you probably would have more unknowns than you have data. The other is that even when you have parameterized it like this, you say, well, I got lots of data, Sure, you might have, like, the total number of data you have might exceed the number of model parameters, but actually a lot of those data might be linearly dependent. And so what you're really needing to have is data that are sort of linearly independent in order to provide extra information. The last thing is you say, well, you can't fit the data, so you add more, and you forget about trying to fit the data. You just try to fit the data as well as possible. You can't even find a single solution to your problem, so you just try to find a minimum. In cases like that, I mean, it seems that you either haven't parameterized finely enough, or your algorithm is not sufficiently good to, to find it, because there should actually be a solution to the problem, unless you've got data that are kind of inconsistent.
It has noise that's consistent with the model.
So I think what we're going to see is most of those things kind of coming out. The question, I think, from the seismic perspective is whether you only need to worry about misfit to the data, or whether there should be other information in there to try to get you a particular kind of model. That's really that really is kind of an essential issue. In virtually all of the things that we'll look at, we're never going to be able to fit the data exactly, because noise can make things inconsistent. But at the same time, even in trying to fit the data to about as well as we think they might be, there's actually a huge number of solutions. And that is actually what happened in that example that I showed you for the DC resistivity. Those models did not fit the data exactly, but they fit the data to within a degree that would be acceptable. In other words, like, okay, that's a good fit to the data. And yet the models are very, very different. So let's look at an example here, just a bit more complicated. So it's a 4-parameter problem. We've got M1 through M4, and I've got 2 data. So this combination gives 6. This combination gives 2. So they got 4 unknowns, 2 data. So there's non-unique solutions, right? And so here's 4 solutions. So there's one that's just a constant, and then there's these other guys. So now I got 4 solutions. I want to choose one. So I want to kind of get to the idea of the rulers. One possibility is that I could just basically make a ruler that kind of measures the size somehow. So we need to have a ruler that could measure either a length or some characteristic of that. We're going to refer to that as phi sub m. So this is going to be our metric. This is going to be the thing that we're going to try to minimize. And then it's the question of what this is. So for instance, it could be the smallness. Like what's the sum of squares of all of the elements? So if we just looked at something like this, then that would be one way that we could judge things. And so that's just looking essentially at kind of like the energy. The other possibility is that we could look at kind of the variation of the elements, or try to minimize the distance between successive elements. So that kind of makes a solution that's sort of smooth or flat if you kind of minimize first order derivative. So this would be the sum of squares of differences between 2 adjacent elements. So if we did that here on the numerical example, if we found what we call the smallest model, minimizing the sum of squares, then actually it turns out it's this second one in here. The value of phi m for these four models is given by this, and the minimum is this answer B as a value of 7.29, and that is shown by this curve here. So we're looking at these successive orange points here as being the solution. Okay. If we chose a different metric, let's say we chose this smoothest one, we're minimizing the variation of these successive elements. Then in that case, the solution that is just constant here, that it has a value of 2, is actually the one that minimizes that. So we've got 4 models here. If we chose this norm, we'd pick out this solution. If we chose this norm, we'd pick out that solution. So that's kind of how things are going to go. There's going to be always an infinite number of these. We're going to try to pick some kind of model norm or some metric for measuring the size of these elements, and then we'll choose the smallest. So what are the things that we can work with? Well, there's a whole host of them in the app that you can work with. These are the ones that are available. So you could minimize the square of the function. You could minimize, you could introduce a reference model and then minimize the deviation of the model from that reference. So that could be something. You could actually ask for just something as smooth where you're minimizing the energy of the derivative. And you could also have a combination. There's no reason why you couldn't have something here that makes it close to a reference model and also makes it smooth. So in many problems, of course, we have some kind of a reference model. In fact, Soggy this morning was showing in the inversion of the MT data and CSEM data, successive inversions where you invert one data set, you get out a model, and then you use that as initial and reference model for another one, and then you can kind of iterate your way through. So kind of successive iterations, and here's where that reference model plays a real role.
In just a comment. Mm-hmm. Sorry, I always do a comparison with size because of course I work with size, but in size when we try to get an inversion, usually we add just another model norms. We usually add an L1 norms that introduce a sparse, so we can kind of gain resolution with the outputs model. Right. And so very usual to put this L1 norm as well.
Yeah, so we can do that here. I mean, I've got twos up here, right?
Yeah.
But I could easily put a 1 norm. I could put any kind of LP, LQ. And in fact, some of the work that we've been doing recently, we've got these 2 elements. We'll sometimes put an L0 norm on one of them and maybe an L2 or an L1 on others. And each time you change one of those parameters up here, now you get an entirely different character. This L0, an L0 norm will give you the fewest number of elements. The L1 will also give you something that's sparse. L2 will tend to smooth things out.
Yeah, that's it.
So you really don't need a lot of, in fact, you want to have as few terms here as possible because things quickly get complicated. Well, not necessarily complicated. It's just that you've got too many buttons to adjust, and after a while you kind of don't know where. An important aspect here is that if we're going to combine a couple of these quantities, then there's going to be like hyperparameters that are going to be required, like the alpha S and the alpha X. So we're going to minimize this thing and minimize that, but now, okay, who do you want to weight more? Do you want it to be closest to the weight that makes it closest to a reference model? Is that going to be more important, or do you want smoothness to be more important? And those are parameters that are generally subjective. There's not any way of mathematically determining what they should be. They become subjective. Okay, so now we set there's two things that we've got. We want to find a solution that produces a misfit to the data that's approximately equal to some target misfit. And as we saw this morning, we don't necessarily want to make that as small as possible, because if we do, we're going to be adding a lot of structure that's just due to noise. And we also want to minimize this model objective function that we've got, so that we find the smallest element of all of the candidates here. So then there's a question how to do that. Well, we're going to recast the inverse problem as an optimization problem, where we actually minimize the sum of these two. So we're going to minimize a phi, which is equal to misfit plus beta times our model objective function. And beta is just it's a trade-off parameter. Sometimes it's called a Tikhonov parameter. And what it's doing is it's providing a relative weight of whether you want to be thinking more about the misfit or the model objective function. And our procedure is actually going to be to try multiple values of beta and to find something that misfits the data about as well as it should be, and at the same time reduces this model norm. Here's our attempt to put everything in a totally different context, but still show the same basic elements. So imagine that you're traveling from point A to point B. This slide was made when we were in Vancouver, so we're going to travel from Vancouver up to Calgary, and we've got an optimization problem here in the sense that we want to minimize the amount of time taken. We want to get there as fast as possible, but at the same time, we also want to minimize the fuel consumption. So we don't want to be burning things up. If you ever get an electric car from Tesla or something, then these things are actually going to be really important, because you only have a certain distance between charging stations, and so you don't want to put your car in the fastest speed possible, because you might not make it to the next charging station. So here's how we could tackle the problem. We could think of an objective function which is both time and both the fuel. We're going to add them with the relative weighting of beta. And so we want to minimize both of these things, and they're both a function of the speed. So if beta is equal to 0, okay, then we're just minimizing the time. So we're just don't care at all about the fuel. We just go as fast as we possibly can, and we'll do that. On this axis here, we've got time on the road, and on this axis, we've got fuel consumption. So when beta is equal to 0, we're kind of out here. We've got big fuel consumption, and our time on the road is minimal. The other end of the scale is when beta is really large, okay, and we want to minimize the amount of fuel we're using. We still have to get there, of course, but that's going to put us up at this end here. We've got best fuel consumption, and time on the road could be long. So probably neither of those end things are going to be really what we want to do. We probably want to have some trade-off. We want to somehow be maybe operating someplace in here. So, maybe our problem is kind of readjusted, so we want to minimize the fuel compensation, but we still want to get there in, let's say, 16 hours. Right? That's sort of what we're willing to look at. And so that would be kind of our target that we try to get, and that would put us on at this point here. So as we change beta from something that's really big to something that's really small, then we're constantly kind of following this particular route here. And at this particular point, we actually hit our target value and we say, okay, we're going to go with that. So that we're going to do the same thing now with the inverse problem. And the beta plays exactly that same role. So from our inverse problem, we're going to minimize the sum of the misfit plus beta by m. And so here's our trade-off. Every time we change beta starts at infinity, then we're going to be up here. As beta gets smaller, we progressively go down this curve, and we end up here. So now the question, okay, which beta do we use? Well, we do have one thing that we've worked with, and that is we generated this misfit function, and within that we've estimated the standard deviations of the errors, so that the expected value of that misfit function should be something in the order of the number of data that we have. So we now have a desired misfit that's something in that order, and so we're going to choose beta so that where our final misfit is approximately equal to this target value. So, Saki, can I get you to come up and we'll sort of run through some examples here with the app? So first of all, let me just get a sense, is all of this like completely old stuff to you? Like this is how you operate on a daily basis, or is this somewhat different or something? I don't really know.
You're talking about this introduction?
Yeah, just the whole setup, the way the inversion is going to be set up.
Or it is the first time to see the theory inversion.
Other people?
It's similar, it's the same theory. We use another regularization.
Yeah.
Total variation, Mach 1.
I think it's very good to get a review.
Okay.
But just a small comment on our previous discussion. The inversion problems that I'm used to deal. I agree with all the points that you mentioned. Okay, the number of unknowns does depend, of course, on the cell. So it will define the number of unknowns, the number of voxels that we have to invert. But in a mathematical, just put in the same way that you put, okay, the example that you made was, okay, x plus y equals 2. And then we have this linear function, and any point can have a solution.
Yeah.
The problem that I usually deal in my daily job is exactly that I have like this, okay, x plus y equals 2, and then x minus y equals 10, and then x plus 2y equals 0. So the problem is that I have like 3 linear functions, and they not
cross point.
So okay, so that's the way I think of inversion problems. So it's in the opposite direction of more equations. So okay, I have any point can solve this equation, and then I have the second equation, any point can solve. Okay, so this one is the best one. But then I have this third equation here. So I don't have this common point. Okay, so I have this 3 equation. So maybe I choose a point like here.
Yeah.
And then it's a solution. In the way that I was talking about, okay, I won't find a solution to anyone, but of course, when one of these norms, one of these criteria, okay, maybe the minimum distance between the solution, the minimum energy, the sparsity. So a criteria to choose one.
Can I ask you, within the context of your problem, what is your data and what is your model?
Yeah, I was just doing Excel just parameterization. The ratio between the knowns and unknowns of least square approach in geophysics, taking particular our Lula nose acquisition, it's like 300, the ratio between the one number and other numbers. And think about a seismic experiment of, okay, I put nodes in the ocean bottom, so I have at least 1,000 nodes. I have a huge number of shots. For each shot, I have 4 seismic traces, 4 components for each node. Each trace is like 10 seconds with a 2 millisecond sample. So the number of data is actually the number of samples. So you multiply the number of shots, the number of receivers, the number of samples in each trace. That gives us a big number. That's the data that we have. The number of unknowns is the size model. And usually in sizing, we invert for like a 25 by 25 by 5 meters. That's the volume 1 voxel. Okay. So if you take this is one unknown, just invert for 1 parameter. In the whole model, it will give us like a 300 more data than the number of
and in each of those voxels, there's a P wave velocity, an S wave velocity. And
yeah, but even if you do that, it's like you're multiplying the number of unknowns for 3. So even though we have like 100 more data than unknown, that's the usual. Okay, of course, as you said, if I set my cells to 1 meter by 1 meter by 1 meter, then I move to the opposite side of this opposed problem. The number of unknowns would be great, but that's not the way we usually do things in sizing.
When you solve your inverse problem, do you have enough? Let me trace this back in. So suppose that we've got, let's suppose just a 1D problem, just to kind of think about things, right? And then if I've got a 1D problem just as I had here, okay, where we got all those kind of crazy solutions, I had more layers than I had data, right? So it was very underdetermined, and you saw what happened if I if I tried to fit the data better. However, if I change, and we can probably do this example, so you might kind of figure out how easily to set this up. But suppose I take that same thing, and I say now I'm going to parameterize it differently. Instead of having 100 layers, I'm going to have 50. And now we can push it as far as we can. And then let's reduce it even more. Instead of having 50 layers, let's have 5 layers. Okay, now we're not going to get crazy solutions. We're going to be getting an end result that has something, okay, but it's not going to go absolutely crazy because our inverse problem has actually been regularized by the parameterization. So that is it. Okay, let's set that up. So let's just. Can we do that?
I think I made an assumption. Sorry, I made an assumption we are always dealing with the underdetermined problems. I think there's we can set the same. We cannot go. Yeah.
Well, I mean that's okay. Look, I mean, suppose that we've got this problem. When we had 100 layers, you saw how everything was going up and down like that. If we had a 2-layer, if we said, oh, I'm going to find the best 2-layer problem, I mean, we're going to get a solution out that fits the data as well as it possibly can. It might not look anything like what's really there, but it's not going to go crazy because you're going to have something.
Yeah,
something there.
That's fine.
So here's where I was kind of coming back to a really important point, and that is when you do your problem, even though you cannot fit the data, and you try to fit the data as well as you possibly can. The question is whether the structure that you get out is actually adequate for what you need, or is, should you be putting in, like something that makes it more smooth, or because
we always have to adjust this objective function or this norm, as you
exactly.
We need to think of it very carefully.
Okay, so therefore you still have, maybe it's sometimes you tend to refer to it as under constrained problem, right? So you technically have more data than you have unknowns, but still there's a lot of latitude in there to get many different kinds of functions out. And some of them could be quite wrong, some of them could be right, and you need to have some extra regularization. So, I mean, the other way of kind of thinking about that is that, okay, I do have a lot more data than I have unknowns, but really most of those data are just linearly dependent. They're not providing any new information. But if I look at the number of independent pieces of information, which you could get by looking at how many significant singular values you have in the composition of your matrix, you'll find that that might still be less than the number of parameters. If that's the case, then you still have an under-constrained problem, and you're going to need to have some extra regularization to get a handle on it.
Professor, just a question. You mentioned by showing the L curve or curve that the best beta is chosen one such that the switch of the tier of data and the minimization of the model norm.
Yep.
But to do so, we will have to solve the problem many times to construct this curve and pick the data that corresponds to the elbow of the curve. In practice, when we have a huge problem, to solve this would require this computation. So what's the hint to select these parameters?
There's quite a few ways that you can address this problem. One that we've implemented a lot in our work is actually iteratively solve the problem, but at each iteration will reduce the value of beta. So we'll kind of do a beta cooling. So in that case, you'll start at a high value of beta, you'll have very little structure, and just gradually reduce beta, and you'll fit the data better and better. And at some point, you're fitting well enough, okay, or you simply can't fit it at all.
But the typical side inversion problem is a large problem, so this a number of times would also have a lot. So I don't see how we choose the beta. I mean, I don't know if it's possible to construct that curve.
Yeah, I think that
in a small problem, we can solve it many times and then plot the error as you show across plot between the data misfit and the model. Like the fuel consumption and the time that there is time. But
I think if you consider that a complete seismic migration is effectively one iteration in a full inversion, you quite quickly appreciate that it is going to be hard to do a large number of these. I'm not sure where the seismic industry is with respect to that. You're kind of at that extreme end of the problem. So what I'm showing you here are still tractable problems. Sorry about that. Yeah, so what I'm showing you here is a framework in which we can solve the forward problem and we can do iterations. For the nonlinear problem, we're going to have to linearize at each step and then solve a linearized problem, and then we'll continue to do that and iterate through like a Gauss-Newton procedure. Yeah, the seismic problem has a lot of challenges because it is so big.
Just we could do it. We could set up the overdetermined problem, but the assumption that I made is for the singular value. So I need to choose what is the kind of minimal information. Where is that? Is that a model side or the data side? Because if you do a singular variable competition, then it'll find a certain value. But I think it'll give you an error, but I think there's no problem actually running the other part. So I could, so for instance, okay, so here we got the default setup is 20 and the model is 100, for instance. Now let's say we got just 50 model and then data is 60. Then it'll give you an error, but that's fine. You don't really have to stop there and then just run the other app. Then can show the data. That looks like the data. So you got more data and the less model parameters. Okay. Then you could run the inversion. How do you want to run? Can you just run it? Okay. You run it. And that's done. So here, if the run button is clicked, that means every click it runs the inversion again. So I'm going to deactivate that. Now you're in some sort of like a coring mode. So we actually got 30 to 40 iteration. We want to kind of explore how we did the inversion. So I think that's we are. Let's just walk through that.
Yeah. So here, at this level, you're actually doing pretty good. You're really starting to pick out the bulk structure, and also you're kind of picking up the bulk fitting of the data on this Tikhonov curve that you have. So you're right down at this particular point here. If we looked at sort of our target misfit, then it might have been up over here. So now we're kind of coming down here.
Do you want to see the Tikhonov?
Yeah, can I just, we'll just keep
That's
going.
exactly the kind of problems that I.
So go back.
Yeah, so keep
going.
Keep going.
Okay.
Just want to.
Oh, it's not going to screw up because it'll. Okay. Actually, it does. Right.
Yeah, so that's still pretty sweet. If we had fewer model elements, let's just try it with let's say 5 model elements. Can we do that?
Yeah, no problem. Well, yeah, there's no problem. Just spits out the error.
Well, let's see what happens. But now we only have 5. So now we shouldn't get anything that's really screwing, right? I mean, it might not be right, but it's not going to be going off the edge of the paper.
Okay.
Sure.
One subtlety here is we are inverse priming this. Just that is important for this.
Yeah. So yeah.
Is
Yeah.
with the model we're actually simulating data on is only 5 points. Whereas the example that you're referring to, the true Earth model is actually strictly continuous, right? So we can think of that being very, very highly discretized. And then we are actually trying to use less parameters to represent that. And that is not something that we currently have set up.
Next time.
Anyway, that's what would happen if we have a lot of cells. Then we're going to be able, as we fit the data better than we should, we're just going to have a lot of structure. But if we had a coarser discretizing, so let's suppose the data were still the same data, we're not changing that, but for the inverse problem, then we have very coarse cells. Then things are not going to go up. So in that case, you're basically regularizing the problem by the crown trip.
Like the one perhaps good example of that is West Plains. So the inversion that we showed that was actually a parametric inversion. So that is sort of an example of how you are using your model parameterization. You're restricting the number of parameters, and that in a sense is imposing regularization because you've confined it to a given structure.
Okay, let's just go back to the generic one. And then we'll move on.
We have to start from model, but
Yeah, but just start with the default, that's fine.
model
Yeah, so there's
data.
a model, kernel functions. Okay, so this is where we are on here. We've got some noise that's added. In this particular case, if we had just minimized the misfit, then
Right?
yeah, let's try it. See how it screws up.
It may not screw up.
Okay.
If I do it. Okay, we've done this before.
Okay, so here's now we're going to play around with this particular model for a bit. We've got this structure. We're up here on this Tikhonov curve. So what's going to happen is we're going to progressively reduce the value of beta. At each point, we solve that linear problem, get a model out, compute the data. So we have the observed, the data misfit, and then there's also a model norm. The red curve here, people had asked about it before. So what we're plotting on here is phi m. So this tells you how much, what the size of your model norm is as you're going on. And you notice that as you fit the data better, in general, almost always, you increase this model norm. So you're requiring more structure to fit the data. So there's this, crosstalk between the two. So as we go through here, as we reduce beta, okay, so now we're getting more of that structure in, misfits reduced, and the model norm is increasing. Continue to do that. So this is kind of, you can just stop back here about 14. Yeah. There's sort of a kink in here when we actually plot the Tikhonov curve where we plot phi d as a function of m. Then that turns out to be a place that you could choose as sometimes an optimum value. At this point here, we're just kind of continuing to reduce the misfit, and the model norm is gradually increasing, and we'll see how bad it gets. So it's pretty bad, right? So now we're actually fitting the data pretty well, and just goes out. Okay, so that was the problem, and now we're going to try to implement some kind of a fix. So we've got these two model ones. One is the smallness, which is controlled by quantity alpha s here. So now let's just ask for a solution that is, it's got kind of minimum energy. And so let's now put that into increase alpha s. Yeah, one's fine. So now as we go down in beta, we are influenced by this regularization term, the more protective function, and we just kind of continue down. So here's an interesting point here. So we have an idea of what the standard deviations of the data are. And so we have a value for the misfit function that we think that we should be somehow around that. So that's at this sort of target value here. And that would be maybe a first estimate of getting out a solution that is meaningful. You're fitting the data to about kind of what you want, and you're also getting a model. We might be able to do a little bit better estimating a misfit just on that approximation of the expected misfit. It's a good starting place, but we really want to see if we can push the data maybe a little bit more. So we start to decrease, take another iteration or two, and we're reducing the misfit a little bit. So we're kind of at this point here. Maybe that's getting pretty close to an optimal solution. We're overfitting the data technically, but we're still okay. But if we round that corner, we fit data more than that, then at some point we just start to kind of break up. So that's sort of the overall idea, that you want to fit the data to a degree that is justified by the errors. You don't want to fit it as well as possible. And at the same time, we want to regularize things by putting in some norm. So we could change that norm. We could make this alpha S pretty small and then ask for something that is rather smooth. In this case, just because of how we've chosen the problem, you tend not to notice that much difference. I mean, even the smallest model is actually kind of smooth at this point. So changing this model objective function in this particular case doesn't make a super dramatic difference, but in most problems that we deal with, having that smoothness term built in turns out to be pretty important. I would just make alpha S small and whatever. And we just run it.
I just stopped it at the target misfit. Do you want to go more?
Okay. So here's another solution that fits the data to the target misfit. Is it? Are you there?
He hasn't gone far enough yet. That fits.
Oh, I see. So I thought you said you were at the target misfit. That's good because it looked pretty strange. Okay, so we'll just. So iteration 4 is that. Okay, keep going. Or I see. That's as far as it went. I got it. Okay. So in this particular case, because we're looking for something that was smooth, it ended up at the target misfit after just 4.
So here the difference is if you click use target, the inversion stops at the target misfit. But if you deactivate it, inversion go until the maximum iteration, which is 30. So I think for you guys, like running big inversion, you may not go too far. So you may want to stop at the target misfit, I guess, or a couple more iterations.
Yeah, but in this case, we kept the data regularization parameter is kept constant like 100. Yeah?
It starts. So there's a couple of parameters here I haven't really talked about. There's a starting value of beta, okay, that is provided. by the algorithm. And then at each iteration, beta is cooled by a certain amount. So as you're going to try to slide down that Tikhonov curve, you can reduce it by whatever you want. And at this point, it's reduced by a factor of 2.
So if I run it again, you can see how beta is decreasing. So it starts from 9, 4.8, 2.4, 1.2. And then we got some matrix to choose initial beta. And the ratio is like, it's giving the ratio between your data misfit function and the model norm. So we have some way to estimate that ratio. Like a ratio is given, but like kind of a relationship between them. Okay, so I think that's a way.
What else did we? Yeah, that's. Oh, the other thing that you have is both an initial model as well as a reference model. So we could actually try one with. Let's try a reference model that is. Let's say it's 1. See what happens. So now, so let's just look at this. Just a smallest model component. Let's put alpha s equal 1. Let's put alpha x equal to 0. So now what we're doing is we're trying to find a solution that's as close as possible to 1 across the whole range. And we can see how well we do in that. Is that it?
Yeah.
Didn't change it very much.
Yeah, I think the last, like this part.
The last part.
Yeah, moved up a bit.
Actually, let's.
Initial and reference?
Let's get rid of, maybe that's too extreme. Let's get rid of the boxcar at the beginning. And then just have a Gaussian towards the end.
Oh, okay. So,
Yeah, let's put that. Let's just take a look at that guy. And now do it one with a 0 reference model, and then one with unity. So the reason for that is as we go down deeper, all the kernel functions are kind of decaying. So we're going to have less resolution at that end. So we might see a bigger difference and more of an effect of the reference model.
So that's the 0.
Okay, so that's with 0. So now if we make it, let's make it, actually let's make it -1. That should do something.
Both or just reference?
That doesn't matter, just a reference. I suppose you really had guessed wrong and you thought you want to make a model that's close to -1. So I get, yeah. It's changing it mostly right at the very end. Not overly dramatic at this point. Okay, that's fine. So the things that you have at your disposal are like changing the kernel functions. You've got an initial model, a reference model. You can change the model objective function. Those are all things that will help influence what the final value is. And I think the most dramatic thing is just the effects that you have for overfitting the data. You start to try to fit the noise in the data, fitting the data better than you should, then yeah, you can quickly get in structure that you really don't want.
Is this targeted misfit related to the standard deviation of the data?
Yeah.
Yes,
Yeah.
so we're using the true. So we assign the 5% standard deviation and the floor noise as a 0.02. But you can definitely change if you want the larger noise and 0.5.
But it seems that the best model is get further iteration in the elbow of that L curve, not the standard deviation.
Yeah, I think it could be around. I think that's ballpark.
Yeah, I mean, very often, what's plotted is, you know, you have the Tikhonov curve, which is phi d versus phi m, and it's, you know, it kind of looks like that. It's sort of, it's often sort of a kind of an L type of curve. The phi d misfit, you know, might be up here. That turns out to, I mean, it's a first order approximation, but for many problems, you can actually reduce that misfit, you know, a little bit more, get a little bit more structure out, so you can fit it, you know, a little bit better than what that particular statistic would be, and still, you know, have a lot of structure, good structure. If the point is, you probably can't go out very far on this, otherwise you're going to. There is something called the L curve. If you plot the, you know, the log phi d, log phi m, very often kind of comes out like this. And in this part here, so beta is increasing from, or decreasing, so this is beta is equal to infinity, beta is equal to 0. At this part of the curve here, the Tikhonov curve, you notice that you're getting, you don't need to have very much extra structure to greatly reduce the misfit, right? So that's a good place. You don't want to be stopping any place up here, because you know, like, okay, I can add just a little bit of extra structure and I really reduce the misfit. So you don't want to be up here, and you also don't want to be down here where you're adding a lot of structure, but you're not changing the misfit very much. So somehow you want to be kind of in there, but there's no, you know, there's no textbook that tells you, oh, you should be exactly there or that. What we do in practice is usually try to sweep down so that we kind of like are between here and here, right? And then you look at the various models, which is kind of what we've been doing here, as we sort of go up and decide on a subjective matter, like, okay, which one am I actually going to choose as my best model? That's where we always are. And it's even more so when you're actually faced with field data, because we don't know what the standard deviations, we don't know what the uncertainties are in those observations. So you're trying to provide a sensible guess. So that means that, you know, maybe you're kind of in this region, but you're willing to, you know, fit the data better or worse depending upon where you are. But there definitely has to be some user input, some subjectivity, some understanding about what's geologically sensible and not. Okay, I think that's okay. Okay. So overall, just to kind of summarize, so beta is this trade-off parameter. If it's too large, we're going to underfit the data, so we're not going to get a good representation of data. And there's not enough. We haven't captured all of the structure that we want. If we are sitting up here and we overfit the data, do a great job at fitting the data, but we've thrown the baby out with the bathwater as far as the inversion goes. So we want to be someplace in this kink here. So sometimes it's called the L curve, and you know, it is kind of like an L. And you're looking for the kink, but there's no. These are all heuristics. They're just ways of kind of getting into the right ballpark. But then you'll probably want to do inversions at a number of different values of beta in here and look to see what you got. So somehow to get something that's a bit more optimal. So here's sort of a general kind of flow chart that you can have for how to think about the inverse problem and how to organize yourself. So the very first part, and sometimes this first part can take 80% of the work, and that is just, okay, I've got field observations. I need to know what they are. I need to know all my sources. What are my transmitters? What are my receivers? What's the data? What normalizations are the data? What filters have been applied? What uncertainties do I have? And we need to be able to do that forward simulation. So all of that has to be kind of up front before you even think about doing the inverse problem. And my experience has been that sometimes 80% or 90% of the work is actually involved in doing this. Especially when it comes to working with field data, you've got contractors involved, and just trying to figure out what the data are, what units they are, and if you get those things wrong, then everything else that you do after that doesn't do you any good. So, you've got your polarity mixed up, right? Yeah, so all of this stuff has to be done up front. You need to bring all your geologic modeling, all your geologic knowledge in, any information about reference models or what you know before, all of that needs to be brought in right up front. Okay, then you're ready to go ahead and really start to contend with the numerics. So you need to be able to discretize the Earth, and to solve this forward problem, you need to be able to simulate the data. Once you've got that, then you've got two decisions to be made. First is choosing a sensible misfit criterion. We chose an L2, and usually that's pretty good, but you might choose something that's more, that permits outliers, like Ekblom norm or something like that. So there is some choice about what you actually want to do for, a misfit criterion. And also, if you're kind of working with kind of multiple data sets, you might want to be balancing how you do the misfits in each of them. And then something that is generally, there's not enough attention being paid, and that is really designing your model objective function. What is the regularization functional that you want to use? Because that's actually, for many problems, like the horse that's pulling the cart. You've got two constraints on your model. You've got data, but you've also got a priori knowledge, and your a priori knowledge has to go into this design of your objective function. So what do you know about the Earth? What's your reference model? Are there faults in some places that you could have sharp discontinuities? Are there other places that you want to be smooth? Just everything that you can muster kind of goes in here. And then now you're all set up to perform the inversion. So you hit the go button. Maybe it takes you a couple of days, maybe it takes you just a few minutes. You perform the inversion. Now you evaluate the results. So this might mean maybe you've done the inversion, you have a number of beta values at which you solve things. Here you might reevaluate, see if one of those are good. And the other thing is often looking at the misfits that are available after you feel you've done the inversion. What are the misfits? Sometimes you find that there's regions that are really poorly fit. So maybe there's actually something wrong. Maybe you want to go back and adjust the uncertainties in some of the data. Maybe you want to redesign your model objective function a little bit. But, there's iterations that are required generally to kind of go around here, and especially when you start to think about the non-uniqueness of the problem, you might end up doing a number of inversions in here. And then finally, you exit and interpret your preferred models. So that's kind of like a global framework, and I don't think there's any way of not working through this somehow. Just every problem that I've ever seen in geophysics kind of follow that sort of methodology. So that's about it. So in summary, we take our model, discretize it, have our data equations. We need our model objective functions that are criteria for measuring size, and got our misfit, got a target misfit, got a Tikhonov curve, and we can, if beta is too large, we're underfitting. If it's too small, we're overfitting. So we want to be someplace in the middle. And that's basically it. So that's the linear problem. Most problems that we have in geophysics are nonlinear. And I want to take you through what we do in a nonlinear, because that might actually be closer to sort of the kinds of things that you're dealing with. So let's just quickly do that. Here was the DC resistivity that I showed you earlier. That's a nonlinear problem. What you're seeing here, I can explain now a little bit more. There was an alpha S, so that was a term that made things close to a background. And an alpha X smoothed in the X direction, and alpha Z smoothed in the Z direction. So these are the coefficients, the alphas that are coming out here. If alpha S is equal to 1, so the only thing that you're asking for is closeness to a background, you don't care about smoothness, then you end up with this as a model. So it's very choppy, especially at the surface, and you get this as an image compared to what you had here. Okay, so that's what happens there. If, on the other hand, you just care about smoothness, you say like, okay, I want to find a solution that is sort of smooth in this horizontal direction, and you push that to the limit, then you can actually get out something that looks like this. So these models are all really, every layer is just really smooth, and that's it. That's what you ask for. On the other hand, if you say, oh, I think things should be smooth in the vertical direction, then alpha Z is equal to 1, and now you get something like that. So by working with these coefficients, you can get really dramatically different results. We weren't able to show that with the linear problem in the app, but those kinds of things will happen. And as I said, all these models are fit well. So if we go to the nonlinear problem, which is really what we've been working with for this whole week, we've got the DC problem or the EM problem. Here's an example with airborne data. It's over a kimberlite pipe in northern Alberta. So this is the area of interest. So kimberlite pipes. I don't know, does Brazil have any? Do you have diamonds at all? Have any?
Yeah.
You do, right? Yeah. Where? Which part?
In Minas Gerais.
Pardon me?
You know, Minas Gerais has a huge province of kimberlite.
Okay. So kimberlite pipes, these are explosive events that come up from the mantle. They bring diamond in a stable form up to the surface. There's a place in, well, there's many places in Canada that have these kimberlite pipes. We were looking at one of them. It's called Fleet-Choke. And there was multiple data sets, electromagnetic data sets that have been run over them. And we're interested in inverting them for a variety of reasons. If there's time tomorrow, I'll go into that. But at this point, just want to show you, an example. So we've got DIGIM, so that's a frequency domain system, and here's the quadrature part at 56 kilohertz. And then there's a BTEM, that's a time domain system, and this is a map at 90 microseconds. So these were two surveys that were taken. Then we got our Maxwell's equations that we need to solve. In one case, we're going, for the resolve system, or the DIGIM system, we're going to solve it in frequency domain, and in the BTEM, it's a time domain survey. So what's the procedure for doing that? Well, we first of all have to solve the forward problem. So that means we need to discretize either frequency or time. So we take our volume, discretize in frequency or time, and then we have to discretize in space. So that will depend upon whether we've got 1D or 3D. And then we've got a large system of equations, and then we've got many transmitters. So every time we move a transmitter, we've got a new source, we've got to solve it again. So now you're back to the seismic problem, right? Every time you change the location of the source, you've got to solve a whole new problem. So in the time domain, we've got Maxwell's equations that look like this. We've got boundary conditions, and we have initial conditions. So we need to solve this in space and time. Then we got Maxwell's equations. So we have to discretize those onto a mesh. And in this case, we're going to put the fields on the edges and the fluxes on the faces. And each cell has got a constant physical property, sigma mu. So these are the differential equations, but then when you discretize them, you end up with matrix and vector equations that look something like this. So the capital C is basically a curl operator, and this capital M is really the bulk representation of this physical property. And so you're able to write functional equations in terms of matrices and vectors, and then to solve that. To discretize in time, we had a time derivative, so that means that we're going to represent that as something at time 1 minus time 0, and separate out the equations that way. So we get this matrix system ultimately that looks like this. So we've got a matrix A times U. U would be the fields that we're interested in. So maybe they're the electric field. And then we got another matrix B times the fields at the previous step. So the fields at a previous step fall into, kind of act like a source for the next time step. And then we've got that system solved. So that can be a big system. And one of the things that has been very important for the kinds of problems we're doing is that the mathematical community has shown how you can take big, large, sparse systems like this and factor it so that you could write A as being like an L transpose. That turns out to be an important part. And then we've got a time step. So what that means is that we've got fields at different times that need to be solved for. So we've got this system here that needs to be solved at each time. If we don't change the time steps, then we can factor this once and use that repetitively to solve for this equation. And in the end, the total computation time is given by something that is that you could you can figure out. So time to factor the matrix, and then the number of times you actually have to solve versus the solving time of each solution, and then the number of sort of basic factor, well, the time groupings that you're using for the whole time problem, which is usually anywhere from 5 to 10. So that's you could appreciate that that's a challenge. So we need to do that, but that's just solving the forward problem. What about the inverse problem? So the inverse problem, we're going to have to contend with this chart, but in solving the inverse problem, we're going to set it up in the same way that we just walked through with the tutorial example. We've got a misfit, got a model regularization, and we're going to try to find that's beta and that particular solution that works. And then the general nonlinear problem, we're going to tackle it by what's called a Gauss-Newton approach. So here's what we want to minimize: the sum of the misfit plus the model objective function or the regularization. So if we're going to minimize that, we're going to take the gradient. So if we differentiate this with respect to the parameters, then we get this as the gradient term. The J in here is the sensitivity matrix. So this tells us how much each datum changes when we change an element of the model that we're looking for. So that's the J. And we're going to try to make this thing equal to 0. It's a non-linear problem, so that we're going to have to iterate. So we're going to do a Taylor expansion about the model that we're currently at, and then take a first order Taylor expansion, and then this is the equation that we have to solve. So this probably looks very familiar to you, because basically we've got something like a J transpose J, so that's telling us something about the sensitivities for the perturbation, and then we've got a regularization term here, and we've got a beta. So probably anybody who's done an inverse problem has seen something that looks like that. On the right-hand side, we've got the gradient. So we solve this for delta M. And then we're going to add that to the model that we're currently at to get an update. The number of forward modelings that's required, we're going to use a conjugate gradient scheme to solve this. So that means applying this matrix onto the right-hand side. So that means we need to be able to multiply J onto a vector and J transpose onto a vector. Each time we do that, we have to do, it's effectively another forward model. So here's where all of the computations kind of come in. We have to solve this system and solve it through conjugate gradient algorithm. Every time we multiply J onto something or J transpose, it's a forward modeling. So the number of forward modelings, and that's the key, is basically 2 times the number of conjugate gradient iterations. So maybe that's 20. So let's imagine we're doing 20 steps in this Gauss-Newton. And then this is basically how it's done. We start off by choosing a beta knot, so that's our starting beta, and we choose our reference model. And then, so we evaluate by the gradient and the matrices, and then we just do a large outer loop. So from 0 up to the maximum number of iterations. At each iteration, we're going to solve for a delta M. Maybe that's good enough, or maybe we actually need to do a line search to kind of update that. So the updated model is what we're currently at plus some perturbation. And then we're going to exit if we fit well enough or if we're not making any more progress. So I think that's kind of pretty standard for anybody who's done a nonlinear version, especially with Gauss-Newton, all of this with the The thing that's challenging for our electromagnetic problems, and is even more challenging for the seismic problem, is like just how many forward modelings you need to do and how expensive it is to actually do that forward modeling. So if we think about that airborne example I've just done, or just doing, so the number of transmitters, so let's suppose even 1,000 transmitters is still not a huge number. Number of time steps might be 50. Solving a particular Gauss-Newton time step requires 20 forward modelings, and the number of Gauss-Newton iterations is 20. So if you put all those together, then the total number of times we have to solve Maxwell's equations on this 3D is about 20 million. So it's a serious amount of computation. Now, of course, you can split this stuff off onto different processors if you've got cloud computing. But even if you're able to get the solution time down to, let's say, a second, then if you have 100 processors, it's still 55 hours. If you've got 1,000 processors, it's 5.5. So you're just simply up against a lot of computing for the stuff that we're doing, and then come back to your problem for the seismic, and it's even worse by another order or a couple orders. But that's where we are, and it's really only been in the last 3 or 4 years that we've been able to kind of tackle problems that are this size, and that's why the examples that I'm showing you here are really only been able to be produced within the last few years. Some of the important things, and Lindsay will talk about it within the context of the MT, is your mesh. So whether you got a 1D, 2D, or 3D problem, you're going to have an appropriate numerical mesh on which to simulate the data. In our case here for the airborne EM, which we've seen so much, you actually you kind of need to divorce the forward modeling mesh and the inversion mesh. So for the forward modeling, you could maybe use an octree mesh that's got something that's a smaller number of cells. So suppose that here is your inversion mesh. Maybe it's got a million cells in it, whatever. But if you have designed also a local mesh so that you could use this for forward modeling, and every time you move the source around, you've got its own individual modeling mesh. Then you can compute the forward responses on this and then use those and solve the inverse problem on the global mesh. So we're divorcing the forward modeling mesh with the inversion mesh. Inversion mesh can have a large number of cells. If you can manage to solve the local problem using 10,000 or 15,000 cells, then you can solve that forward problem easier. So that's what allows us to do this. So the advances, the direct solvers that we can factor the Maxwell operator, semi-structured meshes like octree allows us to reduce the number of variables, separate the forward and the inverse mesh, handling the sensitivity matrix, and really access to a whole bunch of cores. We put all of that together, allows us to solve the frequency or the time domain problems. And in this case here for the airborne data, we're actually able to combine the frequency, time domain data, and get a 3D conductivity model that was representative of the area. This is a plan section. So there's 2 regions here. There's actually 2 pipes that are coming up. This one's really more conductive than this, and a cross section. They look like that, so it outlines both of those pipes. So that's about That's about it. I think the important points here of this is that you get a sense for how to think about the inverse problem, understanding the non-uniqueness, formulating the problem as one in which you've got a trade-off between misfitting the data and structure that's in your final model, and having an idea about, okay, how, if you've got a bigger problem, nonlinear problem, just, these kind of what's actually involved in doing that. Not going through the details, but just still gives you a sense. And ultimately, everything resides in your ability to do the forward modeling. If you can solve the forward model quickly, then you can do a very big inverse problem. If it takes you a long time to solve the forward problem, then it could take you a much longer time to solve it. So I think that's probably a good place to stop. Let's have a quick cup of coffee, and then we'll take you through some stories. Yeah, so
And you can do
yeah. Okay.
Sorry, you were asking me something else. No, it was. Maybe I was too sleepy.
So do you guys know what's going to happen at this barbecue event tonight? Well, it's a celebratory
have
event.
directions. Have directions.
I think we've got the name of the play.
I have the address here. If you want. I have the address.
Oh, okay.
If you want. Take it down.
It's a car wash.
No,
Saturday evening.
Is that what we were talking about earlier today?
Yeah. But it's not the Brazilian barbecue.
It's 2000 Lions Avenue.
It's St. Arnold or something like that?
Yes.
Okay.
You know?
Well, I have the email as well, I think.
Oh,
So,
I think
I think it's on there.
yes.
Okay.
So does anybody know what we can expect?
No, I never went there.
Because it's supposed to be a big celebration. They've got,
Yes.
you guys represent 150 students or something that have come through there, right? So,
But I think the party is bigger because we have to make the registration. I think they try to measure the amount of people.
I believe it's for the students and professors of all summer courses that they did during the summer in the university. I don't know how many.
Yeah.
saying for
Oh, yeah, most of the professors are gone, are they? I don't know.
I think they go. Acho que o Dom ia, né? O Dom,
Sim,
a
acho que o professor
Edmina, Dom, Edmina.
You want to work here?
You were trying, yeah. Yeah, did you try? Yeah. Oh, okay. And then. Here we just set that as well. So that's what, here that's kind of confusing. Just that step. Because that's all. Oh, okay. Oh, that's nice. Slowly increasing. So, I think I changed it. Oh, there we go. Yeah. Okay. Oh, there we go. So interesting, we're losing that. Yeah, so we can get rid of the DC.
Good, you're still on. Just FYI.
Did you want to use this, Darlene?
I think so. That's not good. One sec. Yes.
Especially as expected.
True. It's better when they do, but you know.
Oh, yeah. Next time.
You need to do everything twice, right?
Yeah.
I'm super itchy. Today I found it quite bad. We'll have to see at the grocery store if they have, I'm sure there's Afterbite or something like that, which I would benefit from. Afterbite. My knee is like really red.
Is it really?
Oh, I must have gotten 7 or 8 bites like right in here.
Oh, dear. Well, that's like 2 days ago.
Yeah.
That's a long time.
It is a long time. Texas mosquitoes have real bite.
They're strong.
Yep, they.
Well, Texas, right?
Oh, true. If you want to launch it on mine and both of you play, you're welcome to fiddle on my computer.
It's not gonna. Help yourself.
Can't say no to the boss.
Now, like we'll change later so that you can actually set the number of parameters. So. Yes, basically just bump up the Q.
So we still have one that's got. Oh, I see it. It's not. It almost goes to zero area, right?
John Lehman's site must have gone down or something.
What happened?
John Lehman's site, the TGE.
Yeah. Right. I'll ping him later.
You might have moved it.
Oh, I think that can you see? You run into this one.
That's gonna be 5.
One more thing, if you guys want to. I updated the slides from the future, like the summary in the future this morning.
Oh, okay.
So if you want to flip through that while I'm talking, that might also be. Absolutely.
So I was looking at this equation. So you see that
See what?
this,
Oh, I see.
yeah, you think that you could just click one time, take a run, or is there, or does this thing apply to?
In this case,
If you want, you see what happens?
Yeah.
Also, when zero, zero, t, that must be the t.
Oh, I see.
So you go back to.
I think Z needs to be larger than 0, greater than 0, and T greater than 0. Because I think that in this case, you can double check with on the GeoSci.
Yeah.
But I'm pretty sure that.
This is for half space.
This is a half space. But Z, the plane wave stuff, is Z with respect to the surface of the Earth, or is it with respect to the source location?
Oh, I
So
was
they're pointing out that, like, this guy is.
when z is 0, h is always 0, no matter what t matter. So the z, there should be condition on z and t, right? Because z and t cannot be both 0. In that case, it's not defined 0 divided by 0.
Well, we're quasi-static here, so
Assuming T is.
Allowed.
yeah.
T and z allowed.
Not sure. Z should be okay. Go Z.
But if Z is 0, then this is 0. Always 0. That's not right. 0 all the time. If Z is 0.
I think that's okay because we're starting from 0, and then we're putting this as a boundary condition because delta function is 0 to 1. And then when z is equal to 0, that's your starting point. You start from 0. Well, like
I think
there's no surface. Like it's just we're just making a system where we're starting from 0.
So it's in a hole. It's in a hole.
No, I think it's a boundary of the problem. There's no now here. There's no source.
You mean like
It's a plane wave. It's a surface wave.
surface of a house.
Right, but our plane wave source is on the surface. Right?
Yeah.
Yeah, so in this case, you would expect, like, we set the boundary condition so that, like, our Earth is actually,
Mara, thank you. I texted.
You're welcome. Thank you.
and here is actually where how we apply the current sheet type source. So we've specified here that we have the current sheet on the surface of the Earth. And
We'll
so
meet
in this
tonight.
case, we won't have to specify it. So you like set up an empty source on the surface. But
I think so, yeah.
Yes, I think it's more like a secondary field. That's easier. It's like H
So
naught.
the bottom line is there should be a condition on Z here, right?
Yeah, so Z has to be,
Larger than 0.
Larger than 0.
Yeah, that's what I'm trying to get.
yeah,
Larger
yeah,
than 0,
yeah.
right?
Z has to be.
Okay. Oh, that has to be
Yeah.
So we actually like derive that in the initial sense.
Yeah, I'm going to. I was looking at it because just now I was asking you why they. Remember I was asking.
Oh, I see.
You told me that because the whole space versus half space. So I went back and took a look at these half spaces and tried to understand what would happen in whole space. Remember our conversation?
This is not quite like a.
It's not half space.
Yeah, I think it's more like a boundary value problem. So it's a plane wave. So I'm not sure if we can make a good analogy there, like a whole space.
No, I'm not trying to make an analogy. I'm trying to see. Remember our concept yesterday? The diffusion for that whole space, the electrodipole, is different from all the other diffusion we have been talking about, right? Because the peak does not move. So you told me that is what the whole space thing. Right?
So just if you actually look at that electrical dipole and whole space, the peak doesn't really move that like a move. So the peak.
It'll stay
It'll
right.
stay there and then just
Yeah.
diffuse away,
Yeah.
and then once you got half space, it propagates downwards and upwards. Right?
Yeah.
So I think here's okay. Why is that? Why whole space? The peak doesn't move. That's basically his question.
Well,
completely analogous to our magnetic dipole.
Yeah.
There's no, I mean, symmetry says there's no way for it to move, right? Because it couldn't move right, because otherwise it should be moving.
Yeah.
Just simply.
Yeah, from symmetry, yeah, it's
simply
just
decays
there.
it.
But
But the moment that you put in a boundary here, so that now you prevent currents from going across, then now the situation changes and then the sort of diffuse down.
yeah, so you're right, that's because of whole space. So I was trying to compare the solution from that half space and whole space to see how analytically or mathematically how different they are. That's why I was looking at this.
This is much simplified solution. So if this is a plane wave, you're thinking about like a plane wave. That's the solution. But once you got an electrical dipole, there are a whole bunch of different plane waves that you need to consider. So I think it's not like a quite the same, but yeah.
Well, but that's probably
I think I need to move on to the more
since
I have pretty much got
it's
a
not good.
good
I
understanding.
got
of
good
these.
something like that.
But now I'm starting to notice more patterns, features that I can understand. Probably it's a good point to move on.
Yeah, so go back to
deeper,
work home and
deeper
something
to-
better places.
Yeah,
Exactly.
yeah.
Which should make it, that should make it easier to go back there. Okay, having done this back, and it's easier to go back now.
Os alunos de
The mathematics, because you can put
os
things
alunos do
in
departamento
context. You
de natural science e
can
matemática.
see things.
E o que os lugares?
I think the
Uma
setting
cervejaria chamada.
Yeah, so it's exactly as you said, you just imagine that somehow on the surface here, you put an impulse of current in, right? So you put in, turn on, and then you just watch how that. Wait, maybe
Vai
we'll
dar pra
get.
ver, cara, o Eclipse.
Não, não.
Aqui na zona do hemisfério sul, né?
Só, não, não é hemisfério não, é mais porque aqui é muito para oeste, né? A lua já vai estar fora do eclipse.
Como geralmente ele cai de lado.
É, de qualquer ano que caia, pode dar branco. Do meu eu comprei. Aí eu comprei, mas eu sinto uma massa.
A gente vai na vida do mercado, no alfabete, uma caixinha de 10 dólares.
Se eu fosse o Vasco, o Jorginho pegava o Palmeiras Roger. O Jorginho está se mostrando ser o cara de sempre, que é tranqueiro, cara.
Perfect. So I think that's most people. So we'll get started here again. And what I wanted to start with was actually just a bit of an overview of some of the resources that we've been developing and that are available to you. I know we've mentioned some of these before, but I thought it might be useful to revisit now that you've had some context and maybe some specific questions that you're looking to follow up on. So we mentioned before that we've collected all of these resources on the website, GeoSci.xyz. So this is really a good starting point if you want to go in and further explore any of the resources that we've talked about in this course. So when you come to GeoSci.xyz, there's a few different modules that we have here. So one of the sites you've probably already been to is the courses. So that's where we've got all of these slides available from this week, and we'll post the ones for tomorrow tonight. And eventually we might actually have a blog about this week as well and post some of the photos and things like that we've been taking. And you can see previous courses that we've done and slides in relation to those. So a number of weeks ago, we gave a course in Denmark about airborne EM. And so all of that material is also available. Another set of courses that Doug mentioned and where a lot of this material got started was with the DISC, so the SEG Distinguished Instructor Short Course. And so we've kept this site because there's a lot of interesting resources, and in particular, the blog is something you might be interested to see. So we again have all of the slides and things like that and video recordings of many of the lecture locations. But this is of particular interest because you can actually go and see what other problems related to EM geophysics that people are working on. And so if we come, for example, I don't know, to Vienna, you can talk a bit about the course that went on, who attended. And that's really interesting, is seeing, in some locations, oil and gas is the big hit on the block and what most people are working on. In other places, it's mining. In Europe, it tended to be a lot more geotechnical. And so there's some interesting work that's being done on landslides, for example. There's obviously a lot of mountains in Austria. And so understanding where slopes are stable versus not is really important. And so there's a number of people who have worked on trying to basically use EM to actually get a handle on soil moisture or figure out where clay layers are that might be unstable. And then they can go and monitor and potentially put some things in place to prevent that from happening. It's also been really interesting seeing different connections that are made worldwide. So when we were in Austria, Arnulf actually gave a case history about work that they had done in Mexico. And so we were able to actually present and discuss some of that work about mapping karst structures in Mexico and these cenotes, the sinkholes when we went down to Mexico from a case history in Austria. So it's been really interesting to just get a handle on some of those connections. So we've tried to keep track of all of the different case histories that people have presented. So that's something that you can come on and take a breeze through. So then there's 3 others up top that I want to talk about here. And so each of these are, well, the GPG and EM, those are both textbook style resources. So the GPG is Geophysics for Practicing Geoscientists. And this is a resource that we've used in an undergraduate geophysics course at UBC. And it's starting to be picked up in a few other places. And it's really an introduction to most of the geophysical methods. So it's sort of a once over lightly of each of these methods, what the basic physics are, what you might to expect in the data. And so things like magnetics, for example, which we didn't cover here, if you want to go back and get a bit of a review of magnetics, or if you need to explain magnetics to a colleague, this might be a good place to actually come and just gather some resources and things like that. And so it's got a very similar look and feel to EM GeoSci. And there's also a whole other set of notebooks there and apps with respect to forward modeling that's discussed here. And then, of course, you've seen EM GeoSci. And so this is where we come for the apps, as well as background material on Maxwell's equations, the different geophysical surveys, and all of the case histories. So if you wanted to see the case history that Sagi presented this morning on the Red Sea, there's a more involved write-up with a few more details, as well as links to the original papers, so that you can actually go to the source and get that information there. And then the last site that I wanted to show you here is SimPeg. And so SimPeg is an open source software package. It's written in Python. And that is what a lot of the apps are built on. So most of the forward simulation and inversion is actually done within SimPeg. And so SimPeg stands for Simulation and Parameter Estimation in Geophysics. We have a number of different methods plugged in. So we've got everything. I'll take you to the docs here. You can get a bit of a feel. A good place to get started if you want to just get a feel for SimPeg and what's in there, what you can do with it, is the examples. And so we've got a few that are from recent publications. Those ones are interesting if you want to dive in and reproduce the examples in the publications. They're a bit more involved, so I don't actually recommend them as a starting place. There's a lot of plotting code to make them publication-worthy figures, so the code looks much more intense and scarier than it actually is. So I recommend instead actually starting with a number of these examples here. So you can go and actually see how we programmed up the linear problem. And so step by step, go in and show building a model, building a regularization, and all of those sorts of things. So if you want to see the code that underlies some of the apps, this is a place to go. So in addition to like the simple linear problems, you can see the whole list right here of the number of different methods that we have available. So there's gravity, magnetics, there's DC resistivity, and then we've got the suite of EM problems, as well as some fluid flow. And for seismic right now, we just have straight ray tomography. But there's some interesting examples in both gravity and magnetics. So this was also a recent publication. I believe that's in Chile, actually. So this was an inversion to try and understand volcanic structures with gravity. And then there's quite a number with DC. So if you're interested to go in and see a DC forward simulation or a DC simulation using compact norms, you can come and take a look and see the difference between, so when Doug was talking today about regularization and choosing a model, here we chose a smooth model, and here we're trying to favor a more compact more compact model. And so playing around and looking at what you get out with different norms. And so if you want to get up and running with SimPeg, there are instructions on the site. But perhaps a couple of the things to really point out is that we've got a Google forum. And so if you try to get it installed and run into problems, this is a good place to come and ask questions. And Saudi and I get these emails, as does all of the other SimPeg developers. And so we try to be responsive on there. And then there's also a Slack chat group. So I know Doug mentioned that earlier. So we're on there also all of the time. It's more of a real-time chat. If you have a question with, like, if you have a more involved question, the Google group is where to go. If you just want to sort of get connected, see what people are up to, Slack is a good place to go. Are there any questions with that? No? Okay. So what we're going to look at now, I'm going to show you how to access this, and then I will get up and running with it. So we're going to walk through a tutorial on magnetotellurics and run a nonlinear inversion. And so in this case, you can access this through these simulation notebooks. So far we've been playing mostly with the EM apps. In this case, we'll be looking at examples where code is exposed and it's meant much more to be a walkthrough. And so that's the simulation notebooks. So if you click on that, that'll take you here, and then you can go ahead and launch the binder, like what we've been doing before. So when you do that, you will come to a page that looks like this. So there's a number of different notebooks in here. We tried to arrange them in a way that hopefully makes sense. So there's two here at the top that we go through how to set up a sounding over a sphere. So we showed a number of examples where we looked at either time domain or frequency domain sounding over a sphere, and you can see how the currents change with frequency or with time. And so these examples will actually walk through how we set up the mesh and how we ran the forward simulation. So step by step, what's going on there. The MT tutorial is what we're going to walk through here. These were published as a part of the SEG, the leading edge. Has anybody ever seen the tutorials of the leading edge before?
Yeah.
Yeah. They're a really nice set of publications. It's the only open access publication that the SEG does. So they're freely available. You don't actually have to be a member of the SEG to get access to them. And they're always published with code. So you can actually see, it's meant to be a tutorial on a concept in geophysics, but then there's always supposed to be code next to it so that you can go in and play with the concepts and the ideas in there. So I think Matt wrote a nice one on deconvolution. And so there's some interesting ones in there. So what we did in these notebooks is first we'll set up the 1D magnetotelluric problem. I'm just going to scroll through this notebook fairly quickly. We're not going to go into it in too much detail. But what this one does is we start from Maxwell's equations. And we're actually going to discretize them onto a mesh, go ahead and solve them and compare to an analytic. And so we start from Maxwell's equations, the continuous version. And then we use we simplify to the 1D problem so that we're only taking derivatives with respect to Z. And so we're only looking at the EX and HY components. So it's now a 1D problem. We apply our boundary conditions. And so we're going to put an electric field on the top. And then by the time you get to the bottom, we're going to assume that the fields have decayed. So this is quite common to most discretizations. As soon as you want to discretize, we need to figure out where to put things. And so we have our physical properties. So when we're talking about EM, that's electrical conductivity and magnetic permeability, and potentially dielectric permittivity, if that's being included. And so we put those in cell centers. So you can think of it as actually filling the whole space So here, if we divide up the Earth into cells, we put the values at cell centers, and you can think of this cell, this whole thing, basically being sigma naught, and this whole one being sigma 1. Which is perhaps a bit more intuitive. The other option that we could do is to place it onto the nodes, right? So sigma naught. And in this case, it's much more natural than to connect them with straight lines, which doesn't geologically really make sense, right? If sigma naught is smaller and sigma 1's bigger, you don't expect the conductivity to vary quite like that. When you think about rocks in the Earth, you think about, okay, this is rock unit 1, and maybe this one's more conductive. So we're going to opt to work with this style of discretization where those are in cell centers. And then we use a staggered grid, and we put vectors, so the electric and the magnetic fields, we put those on nodes or on the edges in this case. And in that case, it does make sense to connect them with straight lines, right? We do sort of expect a linear, first order, we can approximate the decays as linear. And so in doing that, we then get to a matrix equation, and that's going to be our system of equations that we're going to solve. And so we have, in this case with the curl, because we're working in 1D, it simplifies down into a gradient and a divergence. And then our magnetic permeability and our electrical conductivity come in as these inner product matrices. And then the fields that we solve for, so we want to solve for the electric field and the magnetic field. So these guys are our unknowns, and everything else is known. And so some of the things that are kind of what we've been trying to do in SimPeg is make it very close to the math. And so when you write a set of discrete equations, we want to be able to actually code that up in a way that's quite similar and intuitive. And so here, the system that we end up setting up looks like this. So in order to get the grad, we get the cell grad. So the mesh, in this case, it's an object. It stores all of the geometry. We'll go into this in a bit more in a second. Stores all the geometry. And then once you have all the geometry specified, we can actually just build those differential operators. So a divergence, a curl, any of those types of things. So we get our matrices, and then we can build up the matrix system that we're going to solve. And so in this case, all we're going to do is stack up, got that gradient, the I omega mu, the m sigma, and the divergence. So that gives us our system matrix. And then our right-hand side, our source term basically, is just that boundary condition on the top, right? We have a plane wave source at the top. So that's all that's doing. And then we can go ahead and solve and compare to an analytic. So that's what this notebook does, is it walks through step by step what's going on and actually turns it into a function. Because we don't want to just solve the MT problem once. We now actually want to reuse this and solve it for a whole bunch of different frequencies or maybe different models. So that's what this does. And then we save that into a Python script. And in the next notebook that I'm going to show you, we're just going to start running with that. Are there any questions there? No? Okay. I know that was a quick overview, but if you're looking at this later and have questions tomorrow, feel free to fire them away. So the next one that I'm going to show you, we're going to walk through forward modeling and show an example of non-uniqueness. Has anybody here programmed in Python before? Yeah? Nice. So when you see this first cell here, and we're importing stuff, some of these are standard Python packages. So NumPy, for example, it's a lot like MATLAB, basically. It keeps track of all of your matrices and matrix operations. SciPy Sparse does sparse matrices. Because we're working with large matrices, so you want to be careful about how you store them. Matplotlib does all the plotting. So the mesh, the utilities, and the solver, that's all coming from SymPeg. So that's specific to SymPeg. And then we bring in a couple other constants. So we're going to work with mu naught and epsilon naught. So those are handy things to have in our namespace. And then the other thing that we're going to bring in is that simulate MT, which is the function that was in the last notebook. Okay, so the first thing that we're going to do is set up a model. So in this case, we'll start with a fairly resistive hash space. We start with a hash space of 100 ohm meters, or a conductivity of 1 times 10 to the negative 2. And we set which frequencies we're going to run the simulation over. So in this case, we have 5 decades of frequency, and we're going to discretize that into 25 different frequencies, logarithmically spaced. Okay, so there's a couple things we need to consider when thinking about designing a mesh. So we need the boundary conditions that we've set is we've got our I think it's equals -1, and then b at z is infinity, 0. Z equals 0 is 0. Here's 1. So we're now going to discretize the Earth. What are some of the things we should be thinking about when doing this? We've set the frequencies. We've set our model. How do we discretize the Earth?
Put increasing size cells downward of the resolution.
Okay, yeah.
And time computation.
Absolutely. Yeah, so we don't want too many cells, right? Because the more cells we have, the bigger our matrix system, the more expensive the problem. Absolutely. And then to your point about being able to expand cells with depth, absolutely. What's nice about the EM problem is it is diffusive, right? So we actually can get away with a coarser discretization with depth. So what controls what our smallest cell should be? What are the things you need to think of when we...
You need to look at the limits of this, the constitutives to get the bigger and the smaller skin depth. And a fraction of the smaller skin depth that you have, maybe a good guess for the, I don't know, like 1/20, 1/, I don't know, a fraction of this skin depth could be the first try.
Yep, absolutely. Yeah, so we often use like at least 4 per skin depth or something like that. Yeah, absolutely. Because we want to make sure that we're capturing, when you say the highest conductivity, we need to capture the fastest changes in the fields. And so we need to make sure that we've got enough cells that we're doing a good job of discretizing that. And then how deep do we need to go? How deep? How big does our mesh need to be?
Depending on our target area of interest, because it is empty data, we can, in principle, we can go all the way downwards. And not only the mental, the dog. But
okay, but what are the things that we've set? So at this point, we know our model, and we know the frequencies.
I think the size, you need to look both. I think both, as Serge said, the objective, where is the thing that you want to map, and also how far will the waves, the fields propagate. So you can look at the opposite sense, the greater skin depth that you have. You don't expect any waves propagate, let's say, I don't know, like 10 skin depth or 20 skin depth. So you take like the minimum frequency or the minimum conductivity that you expect. So you have the greater skin depth, put a factor, I don't know, 2, 3, 10, I don't know, of this. So maybe the minimum between this quantity and the depth of the objective that you want to map, it's first try for the model size.
Yep, absolutely. Because we've set the boundary condition to say the fields have decayed. And the skin depth is telling us how quickly the fields are decaying. So if you're a few skin depths beyond, or like your mesh extends more than a few skin depths, then you're probably in good shape. Yeah, absolutely. So here, now that we've set the frequency and the connectivities, we can actually just look at the skin depth. So in this case, our minimum skin depth for this example is 500 meters. And our maximum skin depth is 1.6 times 10.
So those are your mesh numbers, right?
Yeah.
1/4 in the minimum and 2 in the maximum.
Absolutely, yeah. And so if we sketch out what that looks like for a fourth and 2, and we can try more or less, we'll try that in a second. Then our first pass, we'll look at 125 meter cells near the top where we have those high frequencies affecting us. And then we're going to have our mesh extend at least 3 times 10 to the 5, so 2 skin depths, so that the fields have decayed. And then we are going to be using expanding cells so that we'll have sort of a uniform region in the region that we care about. This is pretty common practice, is if we know that our target is within the top, let's say, kilometer, then maybe we'll use fairly good resolution for that top kilometer, and then we'll start expanding because we're not actually potentially concerned with what's going on down here, what those structures are, but we need to make sure that we've left room for the fields to decay in the simulation. So with most of the apps that we have for DC or EM, we let you play with a model within given bounds, but the simulation mesh is actually much larger so that we make sure that the fields have decayed. So in this case, we just wrote a little wrapper to make sure that our padding, we've added enough padding cells so that we extend far enough. Because here we're exponentially expanding them, so we're expanding them by a factor of 1.3 every time. So if this was a 5 meter cell, for example, then this would be 5 times 1.3. And then here we would multiply by 1.3 again. So they just keep expanding. But then it's not necessarily intuitive to say, you know, I need 15 cells to make sure that I've gone far enough. So here we just have a little function that figures that out for you. So now that we know that, we actually go ahead and construct a 1D mesh. So all that this is doing, with SimPeg, we work with Z positive up. So we start at the bottom of the mesh, which is at depth. And that's where we have those expanding cells. And so we've got our cell size, which was our minimum cell size. Got our number of padding cells, and then that factor that we're going to pad by. And then in the core region of the mesh, we've got, again, a cell size and the number of cells there. So we construct our tensor mesh and also state where our origin of the mesh is. And so we can go ahead and look at that. So if we plot that up, it's just a 1D mesh. That's the bottom of the mesh, and this is the top. And each of those dots is a cell center. And so we've got finer discretization near the top, and then it expands as we go down. And so what I was mentioning before, with the mesh being an object, it has then properties. So we can ask how many cells are in my mesh. So in this case, I have 65. If we look then at some of the first things you saw were things that can be computed on the mesh. So since we know how far apart each of those cell centers are, we can figure out areas and lengths and length scales. And then we can also figure out things like those differential operators. So if we need our cell gradient, we can grab the cell gradient because that's just based on geometry. Okay, so then to make things a bit more interesting, we're going to add a target to our model. So here, our background was 100 ohm meters. Let's add a 10 ohm meter target at 2 kilometers depth, and we'll make it a kilometer thick. When we plot that up, it looks like this. So we've got 100 ohm meters, and then a 10 ohm meter target, and back down to the bottom. So one of the first things that you want to do when you program something up is compare it to something independent. And so here we have an analytic solution for the 1D layered Earth for MT. And so we're going to compare our numerical finite difference solution with an independent analytic solution. There's a couple things in here that are kind of handy if you are using the Jupyter Notebook for coding and exploring a code base. So here, if you actually wanted to read the documentation, we could uncomment this, and the documentation for this MT layered Earth pops up. So that's just kind of a handy thing to see. Okay, so then we are going to have a look at both the numeric and the analytic solution. So the numeric is blue and the analytic is black. And so you can see where the effects of that conductive layer is coming in. We're plotting the apparent resistivity in the phase. And so around about 10 hertz or so, we're starting to see that conductor, the effect of that conductor coming in. And so in this case, just sort of the eyeball norm, if we're looking at each of these, it looks like we've got a pretty good match with the analytic. So first of all, that's a good check that our numerical discretization is pretty good, or our numerical solution is good, and that our discretization is sufficient. And so, you know, if this didn't quite match, one of the first things you might try is like, let's just refine those cells a little more, expand our padding, just make sure that that's not the problem. If it's still not working, then you probably actually need to dive in and figure out what's wrong. So what I wanted to do next is actually show you here, we've got a little widget to explore the impact of the mesh on our results. So again, the analytic is black and the numeric is blue. And we can change both the domain extent and the minimum cell size. So let's start with the minimum cell size. What do you think is going to happen if we make that bigger?
Some points, these dots will not fit the blue line, right?
And what's your intuition about where on the frequency spectrum? Is it going to be high frequencies, low frequencies? Where will it fall apart first? Higher frequency, and why do you think?
Because just vary the minimal cell size, which is the top of the model.
So let's take a look. So right now we're at 125 meters, and we're just going to slowly start coarsening that. So especially in the phase already, right? You can see that just starting to peel off. Yeah. We keep going. Now you can really see, right? And then it's starting to impact the apparent resistivity as well. Also jumping around a bit where we have this conductor, because that is it's affected by those higher frequencies, right?
It's nice to, when we model that, I suppose, of course, you already did things like that, but to see that, because we're seeing just the bad side of the impact of this increase in the minimum cell. But of course, we have a decrease in computational time. So as we model, we always try to get where's the best. Of course, a minimum cell size is great, but then if it demands like 1 month of computation, it's impractical.
Yeah, absolutely.
You need to choose wisely.
Absolutely. Well, and what's nice about a simple example like this too is you can use a 1D to build up your intuition about, okay, I need a solution that's within 5%. I'm okay with it being off by 5%. Yeah. And then you can push and see how far, how big can I get away with. And then that also gives you an idea here, of where you're going to expect things to go wrong. So if I'm going to cut some corners on my simulation, like where might things go wrong? Okay, so let's set this back to 125. Okay, and then let's play with the domain extent. So now what's that going to do? If we shorten If we take our bottom boundary and we move it up, where are you going to see that first?
It's still the lower frequency tends to propagate at a far distance. So if you set a lower domain extension, I suppose the lower frequency will sense it more than the higher.
All right, let's take a look. Okay, so I'm gonna take the domain extent, and we're gonna shrink that. So you can already see right up here the apparent resistivity starting to peel up, right off the analytic. And so in this case, we're getting a higher apparent resistivity, so it's peeling off. And so we're actually doing quite poorly down here. And what's concerning about that is then you can end up looking like there's a new interesting structure that's coming into your data, right? Because this was about to level off, but now there's something interesting, and so that's concerning. Are there any questions with that?
But that true skin depth for the lower limit is from the target area on the bottom of the target area from the surface.
In this case, I believe we did it from the surface. In often cases, yeah, often once you've expanded that far, it's like that distinction isn't too significant. But from this, it was from the surface.
For lower, with low frequencies, would be a high number in kilometers. A very high, very huge number in kilometers.
Yeah, absolutely.
It doesn't change the size of the model because it's a matter of scale. In kilometers, it would be a really huge number.
Yeah, and so that is why we use those expanding cells. One thing that you can play around with too is how quickly they expand. So in this case, we use a factor of 1.3. You can try and expand them faster, but then it's always worth checking against an analytic if you're going to push on that, because if you lose accuracy too quickly, you can actually start doing a poor job of your simulation. So that's another thing that you can go ahead and play with. Okay, so the next thing I want to show is an example of non-uniqueness. So Doug mentioned this example earlier, where we've got the same conductivity thickness product for the layer. And so we're going to have 5 layers here, each with the same conductivity thickness product. So we go ahead and compute that and then figure out what the conductivities or resistivities each should be. So that's all that's doing. We should have a plot here. Yeah. So in this case, these are the 5 models that we're looking at. So each of these, so our thinnest one here is 300 meters thick, and it's fairly conductive. And then we just basically take that, reduce or make it thicker and less conductive. If you do that, these are what the apparent resistivity and phase data look like. And so you can see that, I mean, in all of them, we are seeing that there is a conductive layer. There's no question there. But the spread between these is pretty thin. I mean, if you have really, really high data accuracy, maybe you might be able to differentiate those. But certainly in the phase, you'd be pretty hard pressed to. And if you go ahead and add noise, see if that pops up. So if we go ahead and add noise to the apparent resistivity, for example, even looking, let's see what happens at like 3%. 3-4%. So between that, you can't tell the difference between those. And so without having a priori information, knowing, the top of my boundary or the top of my conductive layer should be at a kilometer depth, then there's no way to distinguish between these models. And so that's important to keep in mind before we start going to the inverse problem. How are you thinking about it? Do it quick, or how are you guys doing? We have one more, one more to show. I can give you a quick overview, or we can go into a couple details.
I'd continue.
Okay. So we showed, Sargi and Doug showed the linear problem. In this case, we're going to do a nonlinear problem. There's a bit more machinery that needed to be developed, and there's 2 notebooks that you can have a look at separately that show, Doug mentioned that we need the sensitivity, for example. So we actually go in and show how to derive the sensitivity, how to test that you've done it accurately, and then also how to compare, make sure you've got the adjoint correct. Because when we do the inverse problem, we need that product of J times a vector, and we need a J transpose times a vector. But J is a large, dense matrix. And as soon as you go to a 3D problem, we certainly don't want to form that. It's too big. And so we always write it as a function so that we compute the product of J times a vector. And so you can do that step by step. But then, of course, that's a little more involved. And so you need, there's a lot of places where it can go wrong. And so it's important to show, to test that and make sure that it's working. So we show a few tests of how you can actually build up confidence that your code is doing what it's supposed to be doing. And then here we walk through setting up the inverse problem. So a lot of this material Doug already covered, but we then also make some connections to what's done in SymPeg, and so how to translate what you've learned today actually into code. So here we're bringing in a few more packages. So we'll bring in the data misfit, the regularization. So that's all familiar from today. We'll also bring in the optimization package because we're going to do the inversion we stated as an optimization problem. So in this case, we're going to work with a 5-layer model. I'll show you what that looks like. And we're going to invert impedance data. So that's that ratio of the electric and the magnetic fields. So again, we set up a mesh following the same principles we did before. So making sure that our finest cells capture those highest frequencies and highest conductivities, and then that our mesh extends far enough to skin depths beyond. This is what the model looks like. So I'm plotting this on, it's on a log-log scale. So depth is expanding logarithmically here. It's a bit different. This is based on a geothermal type example. So we have a fairly resistive top, and then we've got a conductive layer, which might be like a conductive cap to a geothermal reservoir. And then a resistive core. So that's often where you have that hot resistive fluid because it's fairly fresh and circulating. And then there's often a conductor at the base. So gives you a bit of an idea. So then we start off and we're going to simulate data on top of this. And in this case, we'll add some random noise. And we'll plot up and see what that looks like. So we simulate, we've got the clean data shown in the black lines. And then the noisy data are the blue dots around that. So those are the data that we're going to work with for the inversion. And although we've plotted it with apparent resistivity and phase, we're actually going to invert impedances. So here we walk through the SymPeg inversion machinery. I'm not going to go into this in detail, but I'll just give you the highlights. So the mesh we've already talked about, that's all the discretization, the finite volume machinery. So you have all of those differential operators, as well as the geometry and everything. That we use to forward simulate the data. So we set up our set of differential equations, and then we specify some sources and receivers to say how we're going to excite the system and how we're going to collect data. We then use that to calculate our data misfit. So we know what our observed data are, but then we use the forward simulation to predict data on a given model. We combine that with the regularization. So here we'll play with an L2, but there's a few others. You can play with L1, for example. We combine that in a statement of an inverse problem. That's that optimization problem that we're going to solve. So we use optimization machinery to solve it. And then that whole collection we put into an inversion object that's actually going to perform the inversion. And so there's links to the documentation in here that'll point you to what each of these things are doing. So we wrapped all that up in a function here so that we can go ahead and play with all of the different parameters. So we can play with the reference model, the alpha parameters in our regularization, the beta, as well as how we're going to cool beta. So Doug and Sagi talked about, we start with a large beta, and then we can gradually decrease that. And that's an important thing, and that's why we've written so much about it in here, especially when we're talking about a nonlinear problem. So when we talk about a nonlinear problem, we don't necessarily, the space in which we're optimizing isn't always nice. And so in the sense of it can look, we can have all of these local minima around. And so what we try and do when we are using a beta cooling schedule is we try and start with a, fit the regularization really, really well. So we're going to start out and we're going to say, I want you to give me a really, really smooth model. Try and make some progress with that using the data misfit. So we want to, update our smooth model based on the data. And then we gradually just turn down the volume on that regularization. So we try and progress slowly to allow it to slowly introduce structure. If you do too small of a beta, you can get those examples like what Doug and Sagi showed, where you just have a model that jumps all over the place because it can fit the data. All right, so here we're going to start with the same sort of starting and reference model of 10 to the -2 Siemens per meter. And we're going to invert for log conductivity. So why we do that is because we want it to always be positive, right? We know that conductivity should strictly be positive. And then it often also varies logarithmically. We had several orders of magnitude difference in the model that we set up. So that's going to go ahead and invert. I'm just going to shrink that just a touch so it's on one place. And so there's some information that's coming out at you as the SimPeg inversion is running. So you can always see what your beta parameter is. You can see your phi d, so this is our data misfit, our regularization. And then this is going to sum those up, right? So this will be phi d plus beta phi m. And then here we're just looking at basically our step. And so we ran 35 inversion or 35 iterations there, and we can take a look at how the inversion progressed. And so here we can look at the data misfit, the regularization, and then the Tikhonov curve, which is we've plotted the data misfit on the y-axis and the regularization here. That's where you get that L curve shape. The star shows you where our target misfit is. Okay. And so in this case, the first thing that I want to show you is the target misfit. We reached it after 8 iterations. So as we scroll through, keep that in mind, and we'll see what underfitting versus overfitting does in this example. Okay, so this plot is going to show you the model. So the black one is our true model. The blue is the inversion at the iteration here, specified here. This here is showing the Tikhonov curve. So we see our data misfit and our regularization. So we'll print what beta value we're at. Here we show the apparent resistivity, and here we show the phase. Okay, so as we go, you can see the impact of our starting model here, right? This is where we started. Start to introduce some structure. This example that we ran was it's a smooth inversion, so you expect fairly smooth structures coming out. And so this is our target misfit where we hit. And this has done a pretty good job. We've got our resistive top layer. We can see that there are 2 conductive features, and then it goes back. And 2, you can see a bit of insight into your depth of investigation when we start to see the recovered model going back to the regularization. So we see that it's influenced by this guy, but if you extend further and further, it'll start to converge back towards your starting and your reference model. And that's because you just don't have any more information at depth. So the inversion will just keep it at what you've asked for in the regularization. So that's when you hit the target misfit. But as came up earlier, if you look at a couple iterations, right around the target misfit, iteration 9 versus iteration 8, if you had some information telling you what the conductivity of this layer, for example, should be, and iteration 9 does a better job of fitting that, then that's perhaps a better model to interpret on. There's not, the target misfit is not necessarily a magic number. But if we start going beyond that, you do actually see that we're starting to fit into noise. And so even by iteration 13, for example, we've introduced some extra structure here, right? As we keep going, that gets more and more dramatic. And so now it actually looks like there's a whole new layer there that is not. It's because we're fitting into the noise and we're just trying to get all of these details. And even here, right, we're starting to introduce new structure. So then the last thing that we want to talk about here is those alpha parameters. So we showed a bit of an example of what happens when you use a smooth inversion versus a small inversion. So when I say smooth, we're regularizing and we're asking for no large jumps in the first derivative. We ask the value of this cell to be somewhat close to the value of this cell. So we penalize large jumps. When we say a small model, we then say, what is the distance between some reference model? So the first one that we run will be a smooth inversion. And so in this case, we start with the same starting and reference model. And here we're going to use a factor of 5 between these two. Factor of 10 to the 5 between these two. So alpha S is 1 times 10 to the minus 5. And alpha Z, that's controlling the smoothness, that's 1. So we'll run that just to the target misfit, and we'll take a look and see the inverted result. And so before this pops up, take a second to figure out, what do you think it should look like? Okay, so hold on to that. And then now what we're going to do is we're just going to interchange those. So now we're going to do a small inversion and use alpha S is 1 and alpha Z is 1 times 10 to the minus 5. So we're really asking for it to be close to this reference model of 10 to the negative 2. And so we'll run that, and we'll also hit the target misfit. So both of these models are going to fit the data equally well. And so what do you think the difference between these two will look like? What's the small versus the smooth going to look like? Any guesses? Anybody want to draw in the air? Okay, well, we'll plot it up. And so in this case, you can guess which one's which. The blue is the smooth model, very much like what we saw before. And the orange is the small model. And so we're fitting it with these spiky layers. And so again, we're seeing some scary features in here that it looks like there's actually extra layers coming in. And it equally fits the data, but we've introduced these structures that are just not there. And so often when you're actually starting an inversion, it's a good thing to just start with a smooth inversion, see what comes out, and then you can start to put in more a priori information there. But first, see what's supported by the data in a smooth sense. Perfect. Were there any questions with that? Fair enough. I'm sure people are just about done for the day, but if you do want to take a look at these, if there's any questions that come up for tomorrow or in the future, you're free to ping us and we'll go from there. All right.
In the first page of the internet, we have let me know GeoSci. There is a link to TGE that points to the same place with the same thing.
Oh, so TGE, it's a website, I think it might be down right now, but it is a website that is techniques for geophysical instrumentation. Yeah, so it's about instrumentation. It was developed independently, so we're gonna get in touch with him and figure out what's going on. But it is an interesting site on like actually developing like magnetometers, and if you want to use an Arduino to, set up your own instrumentation, there's some.
Because the link is point to the sync segment.
Okay, that's a bug. Thank you. All right.
So I was just going to make one comment then for tomorrow. We're still going to try to kind of figure out a representative question to ask. But the one app that you might want to try tonight is the linear inverse app, one that we were just showing. Sagi was demoing. There's quite a few parameters in there, and it's sort of an opportunity to kind of play with a number of things. And I think it illustrates most of the items that are actually really important. I mean, it's not a simple problem, but the issues that it's addressing carry over to everything, just as you've seen with what Lindsay has said in the MT, that all the things that we were talking about can be manifested here, and in fact, sometimes even more dramatically than we showed in the linear app. So we'll do that, and Roberto, you're still up for talking a little bit for tomorrow, are you?
Sergio?
Yeah.
Oh, is it Sergio? Yeah. And,
I was just asking
You can give us a tutorial.
I'm not sure if I can show PowerPoint. I'll probably just describe the problem I have.
yeah, I think that would be useful. I mean, just even a few minutes just to say what you think is happening, and also your perception of what is going on, and the fact that you've got somebody out there, or a group of people out there, that are putting forth this technique and not being forthcoming in supplying the information that's really required for really scientifically understanding what's going on. And geophysics has never benefited from black magic and people saying, "Oh, I got this great machine. You can't see what's inside of it, but I can pinpoint whatever you want." So I think that would actually be useful. And if anybody else has got some thoughts or questions about the kinds of problems that they're solving, and just even do you think EM could potentially be useful here or not, that would be worthwhile. And also just any kind of general questions about inversion, because as I said, we've traveled around the world. It's just amazing how people can have access to very sophisticated inverse solutions, and yet they kind of get tripped up on some really fundamental things, and then you spend a lot of time and effort and computing power, and you've got nothing to show for it. So want to make sure that those things are solid. Okay. So we'll see you guys all at this party then tonight.
Yeah.
You could show us how to drink margaritas, beer, cachaça.
That's it.